Electrochemistry, study of the interchange of chemical and electrical energy. So, looking at here, obviously inside the batteries, you'll see, if you've ever opened it up, there's lots of chemicals inside, and those chemicals in there change over the energy into electrical energy. And that's what electrochemistry is all about. We all need our batteries, and we love batteries because they power things for us. So, we'll be looking at how they work and the basic structure of them today. First thing we need to do, though, is go back to our idea of redox reactions and half reactions, because this is why we're able to do this. So if we're looking here, why would it be an advantage to be able to split the redox reactions into half reactions and separate them? What can we do when we separate them? What can we see? Electrons, and that's the part where we're going into the electrical energy, is we're isolating and looking at the pathway of the electrons. So in this particular example, we have 5 electrons that are going to be transferred. And that transferring of the electrons is important because if we can manipulate them into a certain pathway, we can end up creating electrical energy. So isolating them into their half reactions, the oxidation, the reduction, we can see the electron flow and we can create a pathway. Okay? And we're going to do this. They're going to end up being separated so that we can create our electrical energy. So in redox reactions, electrons are being transferred. So what is the significance of moving electrons? Moving electrons create what? Electricity, which is also known as electric current or electrical energy. So moving electrons gives us our current, which gives us our electrical energy, which allows us to do work, basically. Provides energy to do work. So that electric current there, electrical energy, very important so that we can power things. So now, as you see here in this diagram, we have the 2 separate chambers going on. And we're going to go over the pieces of all this diagram in just a minute, because we're going to be looking specifically, this diagram represents a galvanic or voltaic cell. And we're going to figure out how these are set up so that we can manipulate this moving electrons in a certain pathway idea. Okay? So first thing before we label anything, go ahead and write down the definition of the galvanic voltaic cell. The device in which the transfer of electrons takes place through an external pathway rather than directly between the reactants. So as you can see, they're set up in separate chambers for that particular reason. We have one chamber over here with one half reaction going on, and another chamber over here that has the other half reaction going on. So in a moment, we're going to label the diagram on your paper and go over the aspects of setting up a galvanic or voltaic cell. Question? Okay. Okay, so here is our picture. Once you're labeling, of course, the 2 different chambers. Now, in between, they're still separated, in this case, they're separated by something we call a porous disk, which I'll go into what's inside the porous disk in a minute. But they are still separated into 2 separate chambers. This up here obviously is a wire connecting our 2 reactions together. And as you can see, the arrows are pointing the direction of which way the electrons are flowing. Over here is the anode, and that's where the oxidation half reaction is going to take place. Okay, so from our previous example, we had Fe2 going to Fe3. So in this chamber, in the solution, you have Fe2 and Fe3 floating around. On the other side, the cathode side, this is where the reduction takes place. So if we're looking at our previous reaction, there was some MnO4 permanganate and Mn2 pluses that would be floating around in the solution. Now, something you should also note that we have pieces stuck in there. Most of the time they're metals, but these are our electrodes that are submerged into the solution there. Okay? Now, the best way to remember which reaction is taking place in which side, there's a simple way to remember it. Say this side is red cat, and this side is anox. Red cat, reduction is the cathode, anox, anode is the oxidation. And basically the anode is this entire side, the whole thing, with the electrode, everything involved would be considered the anode of the cell. Over here, everything with the cathode, the reduction, the electrodes, the solution, all of that is considered the cathode of the cell. Okay? So red cat, anox is the best way to remember which one goes where. Oxidation is in the anode. The other thing you should notice too, that the electrons are always going to be transferring from the anode over to the cathode. That is the pathway. Oxidation, it's splitting apart, giving away the electron. The reduction coming over here is gaining the electron. Okay? So that would be our lovely picture. So what occurs at the anode of the galvanic cell? Oxidation. What occurs at the cathode? Reduction. Electrons will spontaneously flow from the anode to the cathode. As electrons flows, what will happen to the overall charge of the anode? So if electrons are leaving from this side and going out, what's going to happen to this side? This is going to become more positive. It's not very dark, so I'm going to go ahead and write over that. More positive. And if the electrons are therefore going up and around over here to the cathode, this side is going to become more negative. Okay? So, what will eventually happen here, as this side becomes more positive, are the electrons going to want to keep leaving? Because electrons are naturally attracted to what? Positive things. So if this side is building up a positive charge, what's going to happen to your electron flow? It's going to go backwards, yes. Once this side builds up enough positive charge, the electrons aren't going to want to follow the pathway we've set up. So we're going to have a problem here. We have to fix it. So if our anode side becomes too positive, the electrons will want to backtrack and go the other direction. So in order to help this, we insert something between the two sides called a salt bridge. So the galvanic cell will need a salt bridge to be put in there. Now the porous disc can also work as a salt bridge. And the salt bridge is going to help maintain the neutrality of the solution. So we'll let the solution side of the anode build up to be more positive. It won't let the cathode side start building up to be more negative. Okay? The salt bridge is going to fix that. And the salt bridge, if the chambers are separate like this, it's going to be like a tube inserted into both sides of the cell there, completing that, idea of the circuit there. In the other diagram, we would call it the porous disc in between the two chambers, but still the chambers or the two compartments are separated. Now, what are we going to put in a salt bridge to fix our situation so that the electrons don't work for 1 second and then totally start backtracking and going towards the side that's more positive. What could we put in there? Salts. What kind of salts? We want ionic salts, but salts that are going to do what? Completely dissociate. So we call those things that completely dissociate soluble. There you go. And we want salts that aren't going to interfere with the reaction. We want salts that are going to spectate and hang out and float around, but not really do anything. So we want soluble ionic compounds that are going to be inserted into the salt bridge. Okay, and usually the salt bridge materials are made into a paste or a gel. Because obviously if you're inserting it upside down like that, gravity, if it was a solution, would make it fall right into the compartment. But if it's a gel, it will stick, and so we'll still be able to have the abilities of the salt bridge play a role without making it ruin the cell. Now when I say soluble ionic compounds, what kind of compounds are we talking about here? Huh? NaCl would be a good one, except for with silver, lead, or mercury. Why would they want to not use that for those? Because silver chloride, lead chlorides, and mercury chlorides, of course, are insoluble. So we wouldn't want to use that with them. What kind of salts are always soluble? Remember those solubility rules? Those things you like to forget? NO3, nitrates are always soluble, so nitrates are good. What other things are always soluble? Ammonium sometimes can work, but what is the official group of metals that is always soluble? Alkali metals, so group 1 metals, yes. So alkali metals are good. What are some of the other anions that are typically soluble? Chlorine, like I said, doesn't work for silver, lead, or mercury, but yes, for the most part. What are some other, maybe you remember any other soluble anions, always soluble anions? Chlorates are typically yes. Sulfates are typically acetates. There we go, yes. So we could have acetates, sulfates, typically are, I think there's only like a few exceptions to that one, like barium and strontium and something else. And then chlorides are pretty good if you're not working with those other three. So the salt bridges will be created, obviously, to not affect the overall reaction, but they need to be soluble salts. Somebody said chlorates too. Those ones work typically pretty well. But you can't go wrong with a group 1 metal or a nitrate. So you would insert them, or these would be put into the salt bridge. So let's go for potassium nitrate, okay, in the salt bridge. Now, if the anode side over here is going to become more positive, which part of our salt is going to migrate into that particular solution? The NO3s are going to migrate into that solution to help balance out the charge of the solution. So we keep the charge of the overall solution pretty neutral. Okay? So over here on the cathode side, which one's going to come this direction? The potassium is going to migrate this way and keep the charge balanced. That more negative side, keep it more neutral. Now here's a nice little trick where we got these names. Potassium is a type of what? What's the word for something that's positively charged? Cation. Cation. So cations migrate to the cathode.
Oh, that works.
That works, yes. I'm actually thinking that's where they got those names from. And the anions migrate towards the anodes. Is that kind of nifty? So I believe that was number 12. Which way do the ions migrate? The anions are going to migrate towards the anodes, and the cations will migrate towards the cathodes. And what happens if there's no salt bridge or porous disk there?
The electrons will migrate.
So what happens to your cell? It won't work. It'll work for like 2 seconds and then it quickly stops because your electron flow will backtrack to the positive side. So it pretty much will die very quickly without the salt bridge there. Your cell will not be able to move the electrons if you don't have the salt bridge there because they will backtrack towards the positive side and go to equilibrium, and eventually, which is basically the battery would be dead because you have no flow of electrons. So, exercise 1, you're going to start off by drawing your galvanic cell. I want you to look at the reaction here, and you're going to answer some of these questions about it. So let's go ahead and just take a look at our reaction so you can at least build kind of the idea of what you're going to put where. So, in this reaction, I should be able to tell what's going to be the anode and what's going to be in the cathode. So, what's happening to zinc here? Zinc is being oxidized, so zinc's going to go where? It's going to go in the anode, right? And the copper is being reduced. So, since it's being reduced, it's going to be in the cathode side. Okay? So you're going to build yours. You can make up whatever you'd like to be in your salt bridge. And start answering some of those questions below. And we will resume in about 5 minutes so you can hash it out with your table mates and come up with some good answers.
When like batteries die out, do the salt bridges break?
Well, the salt bridges can run out. The solutions themselves could end up running out or completing the reaction, and the electrodes too.
Okay.
But a lot of reasons why, because we can make rechargeable batteries.
Yeah.
And we can make the electrons flow back the other way to restore.
Mm-hmm.
But as much as we like to close everything and be perfectly closed, obviously they're not perfectly closed, so some electrons escape. Sometimes if they are open a little too much, you'll see it oxidizing with the air and you get that crusty stuff around the batteries.
So will it, is it that it just stops working, or is it like...
Well, eventually, over time, because they're not completely shut and closed, you're going to lose electrons, you're going to lose solution, you're going to lose... So they will last for a while. Like those rechargeable ones really do last for a while. And we'll go over the recharging process next time.
Okay.
But that's why they do eventually run out. Regular batteries eventually run out because either their solutions are gone, the salt bridge is gone.
Okay.
They try to maximize the concentrations of everything in order to make it work at the longest that it can. Okay?
Yes. Oh, wait, just kidding. We only used 6 out of the 10.
electron. I reverse them too. So this is the problem with the free response questions that you'll see. They'll give you the basic setup, but they won't tell you which side is which, and you have to identify which side is which based off of the reaction. The other thing to note here is because we have solids in, we have our zinc solid and our copper solids. Those are actually going to be the electrodes in the reaction. Okay. So as the reaction progresses, the electrons will break off, leave through the wire, and they will dump out zinc 2 pluses into the solution. As over here the electrons come over, they're going to combine with the Cu 2 pluses. Okay, they're going to combine and they're going to add on to our Cu. They're going to make solid basically and add on to the electrode there. Okay. Now this is a particular case where the reaction has solids involved. However, some of the reactions like the permanganate one with the manganese +2 or the iron 2 going to iron 3 reaction that we saw at the beginning, those ones have no solids involved. So then you have to make a choice of what your electrodes can be, because you want something that's not reactive, that's not going to mess with your reaction, okay, that can still complete over the circuit here. Okay, so there are some ones that they typically choose to use, and I heard some discussion about them. One of them that you find in your everyday batteries, it's right down the middle of where the positive negative end, that middle section, that is usually made out of graphite, and graphite is carbon, basically. Okay, it's not reactive, but it can act as an electrode. The other one that you'll see a lot of is platinum. Okay, platinum is a mom, but it's not very reactive. Okay, it's very hard. That's why they make, I was telling them to make the diamond rings out of the prongs are always made out of platinum because they're hard. They don't corrode, so you have less chance of your diamond breaking off from the engagement ring. So very good metals to make out of. Gold is another one that's not very reactive too often. Of course, these are more expensive to use, obviously. But you'll see the electrodes more in so like a platinum wire. We have lots of carbon electrodes in the back room too, so those ones will work as well. Okay? So, how do you know which compartment is the anode? So if you were not told what each side was, how would you figure it out? Which one's being oxidized? So the anode, you would look for the oxidation site. How would you identify the cathode? Looking for the one that's being reduced. Yes?
How do you know that the arrows are going from the anode?
Because the electrons always flow from the anode to the cathode. Yes. Because here, since it's oxidizing, it's breaking off the electrons, the positives going in solution, and then the electrons escape up through the wire and go that pathway. Now for the salt bridge here, I chose sodium acetate. Okay, you can choose whichever soluble ionic solid you like, or soluble ionic compound you like to put there. Okay. Now, you also, I know we talked about the AQ ones. You might have some aqueous solutions. Occasionally there are gaseous ones. Those ones are a little bit more complicated in how they arrange them, because to get the gas to go in correctly into the cell is a little bit of a challenge. Where do the cations from the salt bridge go? Towards the cathode. Where do the anions of the salt bridge go? Towards the anode. What electrode will get more massive? Which one's going to be adding on to its mass? The cathode. The electrons come over here. They combine with the ion in solution, and then they form a solid, and that adds to the electrode. So obviously, if this side's becoming more massive, the cathode's becoming more massive electrode, what must be happening over here at the anode? So the solid pieces of the zinc here are breaking off, the electrons go up, but then you break off and you form zinc plus 2 in solution. So that electrode is going to start to degrade and become smaller, less massive. So thinking about that, what happens to the concentrations of each side of the solutions? So if our copper plus 2 over here is combining with electrons to go and form solid, what happens to the concentration of our cathode? Concentration of the Cu2 plus is going to decrease, yes, because it's forming a solid. It's being pulled out of solution. Over here, what's happening to our zinc concentration? It is going to increase because it's breaking off and putting some of it into solution as the electrons escape up through the wire. Okay, so your zinc concentration increases, your copper will decrease. So the anode, like I said, becoming more positive over here because it's dumping positive ions in, and the cathode is becoming more negative because you're taking it out of solution, making it a solid. And that's what the salt bridge is there for, in order to balance out that buildup of the charge in the solutions. So now that we're thinking about all of those aspects, what are some reasons why a battery might stop working? What are we going to run out of? We're going to run out of salt bridge components. Because if they all migrate in and then the neutrality can't be balanced anymore, if you run out of those components, your battery will stop working. What else could happen? So, over here, our copper solution, the plus 2, if it all binds up with a bunch of electrons, it gets depleted, your cathode solution can run out. What else could happen? What else could run out? The what? Which electrode? The anode electrode only has a certain mass to it, right? So if it keeps breaking off and forming the ions in solution, yes, it'll eventually run out. Your zinc electrode over here in this particular example would eventually run out. But the idea of recharging a battery is that you give it energy to make the electrons flow the other way, so you can rebalance the electrode and the solutions that way. But we'll talk about that next time in more detail, how that works. Okay? So for now, we're going to actually look at how to set up and know which components to put with which for these particular cells. Because you can't just put any reaction together. It doesn't really work that way. So here's another diagram of this cell, and the book also has one like this that helps you see the particles very well. So on this side, you can see the zinc is breaking off. Right here, it's breaking off and going into solution. They show you the particles. And this side is showing you the copper's binding up the electrons and forming the solid. There's a couple other things on this diagram I'd like to point out to you. Up here, connecting the wires to each other is called a voltmeter. And it has a numerical value to it. So what do you think that's going to measure? Volts. And volts is a measure of what, though, exactly? The flow of electrons. So if you have a higher number, you have more flow of electrons. You have a lower number, you're going to have less flow of electrons. And if you have 0 volts, that means you have no flow of electrons. There you go. Now, yes, watts and there are other measurements of electrical energy, but in this particular case, we're going to be looking at volts. Another thing to note about here is you see these. This is 1 molar here. This is 1 molar here. A lot of your galvanic cells, you're going to be seeing them under standard conditions, where the concentrations of the solutions are going to be 1 molar. Okay? And our standard reduction potentials are based off of 1 molar solutions. So 1 molar, what are our other standard conditions? 1 1 ATM.
64.
Okay, yes.
98 Kelvin.
298 K, which is 25 degrees Celsius. Good. So we'll be looking at them under standard conditions as well here. Okay? So 1 molar is what you're really going to be looking at most of the time. And of course, there's always an equation where you have non-standard conditions, which we'll talk about that too. But we'll be basically sticking with standard conditions for today. All right, so figuring out how to set up our cells with the right components. How do we know, or how are we going to be able to make the electrons flow spontaneously and be favored? We have to look at a specific, particular factor called the cell potential. Cell potential is also known as the electromotive force, EMF. That cell potential is going to tell you basically during the reduction being pulling of the electrons, during the oxidation they're pushing the electrons, and you need to make sure you have enough pull and push force to make the electrons flow. And we're going to determine that from our oxidation half reactions, our reduction half reactions, by calculating something called the cell potential. And it's also known as E cell. Cell potential is known as E cell. And in order for it to be spontaneously or favored, I know you want to hear those words all over again, you have to have a positive E cell. Must be positive or it's not going to work. So you can't really create a battery if you don't have the right components that are going to create a positive E cell. And the E cell, once again, is determined by the reduction pulling enough and the oxidizing pushing enough in order to create that flow of electrons. So we have to look at their potentials, the individual half reaction potentials, to figure out whether or not the components can work together to create a positive E cell. So the electromotive force, that pushing and pulling, is going to create our cell potential. Okay, so how do we calculate our E cell? Well, we have to look at something called the standard reduction potentials. And the standard reduction potentials were found and created off of hydrogen. It's a standard hydrogen electrode, where hydrogen was hydrogen gas placed in the cathode over here. As I said, it's interesting how they can get the gas to participate. They have to have a tube here and they have to bubble in the gas, and it's definitely very complicated. You see here, because this is a gaseous one, you see that the electrode is platinum, okay? But all the other solutions were worked off of hydrogen. Hydrogen was designated with the volts of 0, so that's where their baseline is coming from. So the oxidation or reduction of hydrogen ended up being 0, so everybody else was based off of hydrogen, okay? And so they created a table of standard reduction potentials. So all of the potentials are in the format of being reduced, okay? So the E values are corresponding to the reduction half reactions at standard conditions. And as you can see, this is a nice table here. The one in your book that you're going to be using is an Appendix E on page 1064, okay? And they used to, on the AP exam, give you the whole list and make you look it up. Now they're kind of a little nicer, where they will actually just put the ones that you need in the problem itself. But the standard reduction potentials were created off of hydrogen, the standard hydrogen electrode. Just that's a little note as to where they came from, okay? But Appendix E in your book, as you see, it's a little bit more massive than this one I put in the PowerPoint of the standard reduction potentials. It's an entire page of them, okay? And yes, you'll probably have to be looking them up on your problem set to figure out how to calculate your E cell, because you have to look them up to get the volt values. Now, looking here, these are all from reduction standpoint. As you can see, as we go over here and we go up, the higher the voltage, this one is 2.87. It's a positive one. So the higher the voltage, the stronger the oxidizing agent or it being reduced. Over here, as you see, here's hydrogen's baseline 0. But as you go down here, the stronger reducing agents and their values are all negative. Okay? So as they become, they're better oxidizers basically. Okay? They're better at being oxidized rather than being at reduced. So their reduction potentials are negative. Okay? But when you're calculating E cell is basically going to be you adding the E of the reduction side plus the E of the oxidation side. Okay, so that's how you're going to calculate your E cell. But in order to find the oxidation one, you have to reverse the reactions. So, say for instance down here with this sodium one, okay, sodium being reduced with an electron gives you sodium solid, and its value is negative 271 volts. Okay? In order to make it an oxidation value, I would have to flip it. So I would make it sodium solid going to sodium plus an electron. When I do that, that changes the sign. This now becomes a positive 271 volts. Okay? So when you're looking at your reaction, you look up your reduction. You can just take that one right off the chart. You look up your oxidation, you have to flip it and change the sign. Okay? Then you can add them together and get the E cell. Does that make sense? So if I was putting, say for instance, let's look here. Okay, let me take the sodium one there, and I'll put it with the fluorine at the top. The fluorine reduction, which is quite high, gives you a positive 287. Okay? That's a positive 287. And since if I'm using the sodium as being oxidized reaction, it's a positive 271. I add those together, am I going to get a positive E cell? Yes. So would those two components work together to create an electron float? Yes. That would be a yes. Okay? So this would end up being 5.58. You'd have lots of potential there. Okay? So this one would work because you get a positive E cell. But if you flip the one and you add them together and you get a negative E cell, then that particular set of reactions won't work together. Okay? And we're going to do a couple together at the end here. But let's finish answering our questions, and we'll work some problems on the back. So just like delta H, if you reverse the reaction, what happens to the sign? It changes to the other sign, so positive becomes negative or negative becomes positive. Now, the key word to number 21 is unlike delta H. If you double, triple, cut in half the reaction, what happens to the value of E cell? It's going to stay the same because it's not like delta H there. And the reason why, number 22, this is because cell potential is an intensive property. It doesn't really matter on the amounts. The flow of electrons are going to be the flow of electrons regardless.
The other one is intensive and extensive.
Extensive is like delta H, which does depend on the amounts. Yes, if you burn a log versus burning a twig, the log's going to produce more heat. But here in E cell, it's an intensive property where amount does not affect the overall flow. Okay? Now, if we look here at our chart, which of these substances is best at being reduced? Well, it's going to be the one with the highest reduction potential. The highest reduction potential is up here, and that was the fluorine. Okay? And then if you look down here, which one's best at being oxidized? Well, it's going to have the lowest reduction potential because it's better at being oxidized. And that's going to be lithium down here. Okay? Doesn't that make sense, though? What do they make batteries out of? Lithium. Lithium's in a lot of batteries. It's got a really good oxidized. It's good at being oxidized. So they like to incorporate that one. Why don't they use fluorine, though? Fluorine's not, I don't hear fluorine batteries. Do you hear fluorine batteries?
They're wild.
They're wild?
Not stable.
What is the problem with fluorine being able to be put in a little compartment like that? What does fluorine normally exist as? Gas. So channeling a gas into the battery chamber and making it work is a little bit more difficult. Lithium's HU. Lithium will be, you can easily dissolve it, right? So they can put lithium in very, very carefully and easily. Fluorine, on the other hand, is not so easy. So you have to look for other components to stick in the batteries. Okay? Oh, so E cell is positive. That means it's spontaneous and favored, right? So let's relate that to delta G. D cell is positive. Delta G must be. And KEQ must be greater than 1. Good. So now delta G and equilibrium can be related to cell potential. Okay? So if E cell is negative, though, E cell is negative, delta G is positive, and KEQ is good. And then if E cell equals 0, delta G equals 0, and KEQ equals 1. What does this mean? It's at equilibrium. And basically, once your electrons stop flowing, because either your solutions, your salt bridges, or your electrodes have run out, you are now down to 0 E cell, so you're at equilibrium. When you have a dead battery, it's because it's at equilibrium. All right, so let's look at the examples here, and let me show you how to get started on them. All right, here. You're going to draw an E cell, you're going to draw a galvanic cell, and you're going to label everything and all that. But I need to figure something out here. They gave me both the reduction potentials. And I want a spontaneous favored E cell, galvanic cell. So I have to figure out which one to flip here. Which one do I need to flip in order to make it have a positive E cell?
The first one.
So the copper reaction needs to be flipped. Okay? So first things first, I'm going to flip this.
First things first.
Let me actually draw an arrow instead of, there we go, flipped it. Okay. So what happens to my E now? It becomes oxidation, and now it's negative. Okay? Because I've now made it an oxidation reaction. So if I subtract, what is going to be my E cell now? Well, subtract or add, I guess, because it's now negative. You just add it together. It's going to be 1 point... What?
3.7.
3.47
347.
volts, and it's positive. So now our E cell will work. You also need to balance the reaction. So how do I balance and make the overall reaction? I got to multiply this one by 3. So I get 3Cu plus 3Cu2 plus and 3 electrons. Therefore, I can cancel electrons with electrons and write my overall. So I end up with Au plus 3 Cu plus giving us Au solid plus 3Cu. Okay, so we'll go with the 2 plus here. Okay? So that's your overall balance reaction. And now you can draw in your galvanic cell, identify the anode, and label all of the parts. Once you get done with this one, go ahead and move on to exercise 2. Give you a few minutes, and then I'll wrap up the answers and check your answers.
Yes.
I know.
Your brother replaced
I know, that's what I meant. We meant like cancel them.
Oh, but they were like, oh, like his time.
Yeah, you don't get those. That's what we were asking. We were asking. She said yes.
It's fine. It's a close call on if it's that far. Like it's happening.
Oh, it's like the buildings.
Okay, so as you can see here, which electrode is going to get more massive? The cathode. So the gold is going to start becoming more massive. Okay? And obviously the concentration on that side is going to start to decrease. Okay?
Wait, why did you use NaO3? Does it matter which one you use?
I just picked a soluble ionic compound. Okay?
Can you switch like how to choose your electrode? Like you said like carbon.
Oh, the electrodes. Okay. Yes, in here we do have solid gold, so we would use the solid as the electrode for that side. Over here, though, we have copper 1 and copper 2 in solution. So you have to use platinum or carbon there because you don't have a solid part of that reaction. They're both AQ. So they're both floating around in the solution. So that's why you would need to use platinum or carbon there.
When it's not a solid.
When you don't have a solid, if they're gaseous or aqueous, most of the time they're aqueous, though, when they don't have the solid involved. Okay? So that, any other questions about this one before we move on to the next one?
What would you use? Can you use anything like an electrode if it's like a solid?
No, you don't want to just use anything because you want something that's not reactive, that's not going to interfere. Okay? So you wouldn't want to use, especially like somebody suggested iron, you wouldn't want to use iron because iron can redox.
Yeah.
Okay? So that's for this particular one. The next one, we need to calculate the E cell. So we know which one's oxidation, which one's reduction. So, which one should we flip here?
The permanganate.
The permanganate needs to flip. Good.
Everything else.
So, this now is going to be oxidation.
Oh wait.
So, our cell potential ends up being a positive
It'd be 3H2O.
0.09 volts, which isn't very good, by the way. So I don't know if I'd want to be constructing my battery out of these components, but it still is a positive E cell, so that's good. Something else to notice about what's going on up here in these solutions. What are we in here? But what else is in the solution besides just the water? H. They're both in acidified solutions, so you would also need to incorporate those H's in there, because noting that they're both sitting in a dilute acidic solution. A lot of times the redox need those, H pluses in there. So when you draw yours, you need to make sure you incorporate the H pluses in there, okay? Because they will be part of it. Now we need to balance this one, so what do you need to do? Which one? We need to multiply them both. Which one? This one needs to be multiplied by a, and this one needs to be multiplied by a. Okay, so when you're balancing, make sure you multiply, cancel out your electrons. Yes, I know in the overall balance reaction, it will look like the H pluses are only on one side, but they both are in acidified solution, so make sure that you can incorporate that into your drawing. Okay, so that's another thing to note. What else should you note here? Both of our redoxes here are both aqueous, so what kind of electrodes would you use? Platinum, carbon. Okay, that's pretty much the only other thing that's significant here is that you need to add H pluses to your solution. You don't have to actually put water in there because it is assumed it's aqueous, meaning it's dissolved in water. But you do, when you want to show your ions, make sure you add some H pluses to both sides. Okay? So go ahead and draw that.
Wait, how do you know this? Oh, they're both. I just mean I just want to know if one is a solid, still okay if you use platinum.
If you have a solid, you would use a solid of that particular, yes. Mm-hmm.
So when they're both like ions, do you want to put both the ions in the solution? Like,
Correct. They will both be floating around in there. So yes, the only other real difference here is you have the H pluses in solution. Both components are in solution together of the redox. And if you want to check your balance reaction.
wait, so do you actually need to balance it, or you just need to flip it?
If you're just doing the E cell stuff, you would just flip it. But here it was asking for the overall balance reaction, so you wouldn't need to.
So you need that also.
If it asks for it, yes.
But you don't have to rate how many of them there are in the solutions.
No, you would not need to identify that. And most of the problems, you really aren't going to be drawing them. You're going to be looking at the diagram, interpreting them, and figuring out which side's the anode, which side's the cathode, and then using the numbers in order to calculate stuff. Okay? So that should be the balanced overall. I'm going to check yours. And we will continue on Monday. Any questions? Concerns? Questions? Good?
The first